Okay, in this lesson, we're again going to be looking at hypothesis testing for proportions, but this time we're going to have a little bit different scenario where we are going to put all of our chance of error into one tail. So let's see what that looks like. We have 1,009 consumers were asked if they were comfortable with having drones deliver their purchases, and 54%, or 545 of them, responded with no. We're going to use these results to test a claim that most consumers are uncomfortable with drone deliveries. There's a little bit of a hint here. We need to interpret most to mean more than half or greater than 0.5. So trying to figure out what our p-hat is and what our p is, our sample proportion is the 54% because that was derived from our survey or our sample. Our population proportion is the 50% that we are trying to claim, or that our claim is attached to. Okay, so our claim is that more than half of consumers are uncomfortable with drone deliveries. So we're testing the population proportion is greater than 0.5. And again, we got that 0.5 from most, meaning more than half or more than 50%. Okay, so our null hypothesis, again, is always going to have the equality. The population proportion is equal to 0.5. Our claim is our null hypothesis, or our alternative hypothesis, that the population is greater than 0.5. Okay, so we need to always remember that our null hypothesis will have the equality. Our alternative hypothesis will have the inequality. Okay, so the fourth step is I want you to think about what is our confidence level and what is our alpha, or our chance of error. So our confidence level is 95, our alpha was 0.05, and I believe I forgot to put that on here, that I should have written in here a confidence level of 95% or alpha 0.05. So hopefully I've got that corrected in your copy. Okay, but that is given here. Okay, this is a right-tailed test, and I know that because of this sign here, and I got that sign here, that our alternative hypothesis, the population proportion, is greater than 0.5. I got that statement from this here, greater than 0.5. That greater than definitely tells me I'm dealing with a tail. So this is a right-tailed test. Remember, this is pointing to the right. That matches up with the right-tailed test. Our critical value will be 1.645. And if you want to know how I found that, I could go to our formula page, which you will have available to you. We are doing a one-tailed test at an alpha of 0.05. This is the critical z-score that goes with that. Or we can go back to the activity that we did earlier, where we're looking at all the different breakdowns. We are doing a 95% confidence level test. That means our alpha is 0.05, and this is a right-tailed test, so we're going to go all the way over here. Our curve should look something like this. This 1.64, 1.645 is our critical value that separates normal or usual outcomes from unusual outcomes. So if we land a test statistic that generates a z-score way over here to the right of our critical value, we know that we have something that is unique, significantly significant, and we would reject our null hypothesis. If we end up with a z-score that is in here, no big deal, we will fail to reject the null hypothesis. So if we land with something over here, that is telling us that our sample statistics is generating something that's very unusual that could not possibly have happened by chance, random chance. Okay, so back to our information here. The fifth step is looking at the test statistic. This is the formula, and again, you will have that formula available to you on the formula page. So it's on the side that says hypothesis test. It's the very first formula, the only one that we're dealing with on this side of the page so far. Okay, back to the notes. Once we start plugging things in, remember p-hat comes before the population proportion. So that was 0.54 minus 0.5. The information underneath the radical sign here in the denominator of our test statistic is the numerator deals with our population proportion, and n is 1,009. So once we plug all that in, we get a very high test statistic. 2.54 is much greater than 1.645. So this is our test statistic generated by our sample data. So going down and looking at our three methods, how they should all fit together, drawing our critical value curve here, like we looked at on the previous page, this 2.54 falls in our rejection zone. When we're looking at the p-value, we're looking at if you go to the table, the normal distribution, looking for the probability less than 2.54 on our table would show us 0.9945. Remember, that's the area to the left. We're looking to the right. We're trying to figure out what is this amount right in here. So when we take that away from 1, because it's complementary to the left side, we end up with a really small probability. So that is really telling you that this data is unique, that we couldn't possibly come up with this outcome by chance. Okay, so we look at our third method, looking at a confidence interval, and this really should be a check. We're going to remember, confidence interval uses our sample data. So we're going to be looking at 0.54 for p-hat. Our z-score is going to be plus or minus 1.645. And again, I just want to show you where we find that. Going back to our formula page, we are doing a one-tailed test, 0.05. Our one tail in our test statistic, this is what we use. But I'm looking at a confidence interval is what I'm trying to create right now. And we need to think about, if we have 0.05 chance of error in one tail here, the confidence interval that would have 0.05 in one tail would be a two-tailed confidence interval that is a 90% confidence interval, 0.05 in each tail. So we need to use the 1.645 for this confidence interval. It happens to be the same thing, and that's kind of nice. So I want to point out why we're using 1.645 when it's over here under the two-tail, because that's the confidence interval. Back to the notes. So when we plug all that in, we end up with a confidence interval range of 0.5142 all the way up to 0.5658. Now what does that mean? That means that from this data, if this data is from a true random sample, that we could speculate that the true population proportion should fall in here. If you go back to your null hypothesis that the population proportion is equal to 0.5, 0.5 does not even fall in this confidence interval. It's outside that range. So we have to reject the null hypothesis. All three of these are telling us we've got a rejection zone, we've got a really, really small p-value compared to our alpha, and we've got a confidence interval that doesn't even include the projected population proportion. So our decision would be to reject the null hypothesis, and the concluding statement might go something like this. There is sufficient evidence to support the claim that the majority of consumers are uncomfortable with drone delivery. I want to show you how you would do this on StatCrunch. Thing is, I can't get both screens to show here, so I'm going to go to town here. We go to Stats. We're going to go down to Proportion Statistics, over to One Sample, and down to Summary. That's been the same as it was for the last one. I click on that. Remember, we have to put in the summary data from our sample. So we have 545 said that they were not happy with drone delivery. They were not comfortable with it. And it's defaulted to the hypothesis test. And it just so happens that we were testing more than half, so population proportion is already defaulted for us. But here we have to change this to a right tail. So when we calculate and compute, we end up with, again, that here we have our z-test statistic, which is what we came up with when we did this by hand. And we've got a p-value which is very low, 0.0054. That's less than 0.5%. So for sure, this is a reject the null hypothesis. Now, to do the confidence interval, I'm going to go back and click Edit, and this is what you need to really pay attention to. When I click the confidence interval, remember, we are trying to create a confidence level interval where we have 5% in that right tail. So we need to have 0.05 in that right tail. This confidence level of 0.95 would only put 2.5% in each tail. Because remember, confidence intervals are two-tailed phenomena, or two-tailed events. So I need to change this to 0.9. 0.9 would be a confidence interval that would have 5% in each tail, which matches what our confidence level in our hypothesis test. So when I hit compute, I get these intervals, the same that we had when we did this by hand. We can see that 0.5 is not in that interval. So if the population proportion that we're testing is not in here, that's basically proof or evidence, I should say evidence, that we need to reject the null hypothesis.